Chapter 5, we're going to take a look at energy and its relationship to work and to power and to machines. And the machines we're going to look at are simple machines. Awful lot of information in one chapter. We'll work our way through it one step at a time. First, we need to make sure we know the definition of energy. And the way we're going to define energy is as the ability to create change. The units that we use for energy are joules, named after Mr. Joule, a British scientist who did an awful lot of study on energy and forming it and its different types. Let's take a look at the different forms of energy, some of which we'll talk about in this class and some of which are more appropriate in other types of science classes. Kinetic energy is the first one on the list. Kinetic energy is what type of energy? Hopefully you've determined that it is the energy of motion. The next type of energy we're going to talk about is gravitational potential energy. The word potential, can you come up with the meaning for that or an implication for the word potential? In this sense, in this class, we're going to talk about potential energy as stored energy. So gravitational potential energy is energy stored because of a position of an object relative to the ground or some sort of vertical reference base. Another type of stored or potential energy is chemical potential energy. That's the type of energy we're not going to be focusing on in this class. We'll focus more on gravitational potential energy and another type of potential energy, elastic. Chemical potential energy is the energy that's stored in the bonds of a chemical compound. Elastic potential energy is another type of stored energy. Elastic refers to what type of behavior of an object. Can you come up with something? Elastic refers to the ability of an object to either be stretched or compressed. And so elastic potential energy is energy that's stored when an object is stretched or when an object is compressed. You can think about springs, you can think about rubber bands. The last type of energy we're going to categorize as dissipated energy. Dissipated energy is energy that we can't use to change an object's behavior, to change its position, to be used to make an object change its motion. So it's still energy, and there are many types of energy that we use that we would classify as dissipated energy. But we're going to define dissipated energy as energy that's not able to be used to change the object's motion or position. Shorthand symbols for these different types of energies. I'm going to give you a couple of them, and Ms. Howell and I will be using them interchangeably, and one of us may use one more than the other, and also the equation sheets provided by the AP system may use yet a different one. So you need to be aware of all these symbols. So for kinetic energy, E for energy, subscript K. Another way to reference it is KE for kinetic energy, or just plain K. Gravitational potential energy, again, energy, and the type of this one is gravitational potential, so it would be EG. Since it's potential energy, and if it's one of the two types of potential energy we're going to talk about in this class, we can call it PE for potential energy, and AP uses the symbol U. Chemical energy, since we're not going to work with it, we don't have to worry too much about it. The symbol that would tend to be used would be E sub C for chemical. Elastic potential energy, again, E for energy, with a subscript E for elastic potential energy, and AP uses U with an S subscript. My guess is for stretch. Dissipated energy, energy, and D for a subscript. Equations. We're going to be working with and calculating these different types of energy and showing the relationship between these types of energies. So we need to know what is the equation for each type of energy. We're going to look at the 4 equations of the 4 types of energy we're going to focus on in this class. Kinetic energy, since it's energy of motion, it depends on how fast the object is moving. The other thing that kinetic energy depends on is the mass of the object. So kinetic energy is 1/2 mv squared. Gravitational potential energy, because it's gravitational, it depends on how high above a surface reference an object is, so height's involved. Since it's gravitational potential energy, we need to take into consideration the gravitational constant, and it too depends on mass. So the equation for gravitational potential energy is the mass times g times the height above the reference point. We're not going to come up with an equation for chemical potential energy because we're not going to work with it. For elastic potential energy, we're going to look at something called a stretch constant, and we're also interested in how far something stretches or compresses when we're looking at how much energy it stores. So the equation for elastic potential energy is 1/2 times K, which is the stretch constant, times the change in the object's length squared. So if you look at that equation and you look at kinetic energy, they're very similar in terms of their format, but the variables in the equation are different. Most of the time for dissipated energy, we're going to be looking at energy that's dissipated because of friction. So we're going to look at an equation that involves friction force and how far an object is sliding during this process. So the equation for dissipated energy most often that we're going to use is friction force, its parallel component, times the distance the object travels. One of the laws of thermodynamics, one of the main laws of thermodynamics, is that energy is not created and it's not destroyed. It can change form, it can be transferred, but you can't suddenly create energy out of nothing or have energy simply vaporize, disappear, and not have it. So what we're going to look at is the before versus after picture of energy in a system. So another way to state that energy is neither created or destroyed is to say that energy in a system is conserved. So you have to define the system, and you define the system to make sure that energy is conserved.